The Big Bang, 13.8 billion years ago.
We, CERN, are trying to understand matter.
We built a world-class physics laboratory with the most powerful particle accelerators.
Fundamental research in particle physics not only pushes back the boundaries of our knowledge of the universe,
but also catalyzes innovative technology developments. We built a bigger machine, the LHC, with bigger detectors.
ALICE,
Atlas,
CMS.
LHCb. The scale and demands of our accelerators, detectors, and computing infrastructure
Constantly push the boundaries of technology.
together with our member states, associate member states, and partners across the globe.
We develop state-of-the-art technologies in different domains.
Technology that impacts and saves lives.
When the World Wide Web was invented, we offered it to the world.
1.8 billion websites today run on the World Wide Web for almost 5 billion web users. The technologies and scientific advances behind high-energy physics, through developments in accelerators, detectors and computing, have historically contributed to the field of medical and biomedical technologies.
They also extend to a vast range of areas
Such as aerospace, Industry 4.0, cultural heritage,
education,
outreach, human capital.
and open science. We are a powerful model for international cooperation.
Taken as an example by other intergovernmental organizations and endeavors.
We work together for a common good and are a proven source of inspiration for future generations.
And a model for other international research projects. Did you know that €1 invested in CERN's research brings back 1.8 euros to society?
We have had and will continue to have an impact on all of our lives and on the world around us.
Understanding our universe means going further than outer space. We are CERN,
and we are going back to the origin of our universe
pushing science
and pushing technology.
Called quarks. An extremely strong force, transmitted by so-called gluons, holds the quarks together. The force between the quarks is so strong that it has never been possible to separate the quarks from each other. In ordinary matter, quarks can only exist in this prisoner state inside protons and neutrons. But where does all the matter come from? The history of the universe starts with the Big Bang, about 13.8 billion years ago. It produces all particles in the universe in less than a millionth of a second. For an instant, these particles form a hot and dense soup called the quark-gluon plasma, where quarks can roam freely. Scientists are keen to study the properties of this primordial state of matter, since it's crucial for our understanding of the birth of matter in the universe. At CERN, lead nuclei are traveling through a network of accelerators, where they go faster and faster, until they reach almost the speed of light inside the LHC. By colliding the nuclei, scientists recreate conditions that existed in the first instance of the universe. Inside a tiny fireball, thousands of newly created particles form a droplet of primordial matter, the quark-gluon plasma. But the fireball is extremely short-lived. As it rapidly expands and cools down, free quarks start to group. Protons, neutrons, and other particles emerge from the collision. The study of the production of these particles reveals the properties of the quark-gluon plasma. It is 30 times denser than an atomic nucleus, and even very energetic quarks are quickly absorbed. But for photons, which are insensitive to the strong interaction, the plasma is transparent. The plasma temperature is 200,000 times higher than in the core of the Sun, and it behaves like a perfect liquid without any internal friction. The study of the lead-ion collisions needs an enormous three-dimensional digital camera that surrounds the collision point. This is the ALICE detector. It records the direction and energy of particles emerging from a collision. By analyzing millions of collisions and comparing them with theoretical models, we can learn more about the properties of this primordial state of matter. The ALICE detector is installed in a cavern 56 meters below ground. It is 16 meters high, 16 meters wide, and 26 meters long. Its weight is 10,000 tons, more than the Eiffel Tower. The ALICE detector consists of several components for measuring charged and neutral particles. A huge magnet produces a field of 0.5 Tesla, forcing charged particles on a curved path. They leave signals in some of the millions of sensors in the tracking devices. Computers identify tracks by connecting these signals and determine the energy and type of each charged particle. The energy of electrons and photons is measured in so-called calorimeters, which are located further outside. Muons are similar to heavy electrons and are detected in the muon spectrometer. A large dipole magnet bends their tracks, and several detector layers record their position. The data from all collisions are recorded to mass storage, amounting to many thousands of terabytes every year. Hundreds of scientists from the ALICE collaboration analyzed these data. They are using the computer power of the LHC grid, which consists of several hundreds of thousands of computers distributed all over the world. The history of the ALICE collaboration starts in 1993, when the letter of intent is submitted to the LHC committee. The approval process takes almost 4 years and requires a number of detailed design reports. Since 1997, more than 1,600 scientists and engineers from more than 170 institutes in more than 40 countries have designed, built and operated the ALICE detector. Since the start of the LHC in 2010, ALICE has studied the quark-gluon plasma. It has measured the expansion and cooling process with unprecedented precision and observed how different particle types are produced and interact when they pass through the plasma. Over the next years, the ALICE detector will continue to take data and to extend its performance. Thousands of scientists from all over the world are looking forward to new discoveries about how the universe evolved from its first moments of existence.
हमारे माँ का कितनी परमिशन लोगे यार। अकेला मैं बैठा हूँ, होस्ट के आने का ज्वाइन कर रहा हूँ। तो ही होस्ट बन जा। क्या दिखाए उनको? वो हमें टर्न दिखाने वाले। मैं क्या दिखाऊं? पानी पूरी की प्लेट उनको। वो तो है। बता। આવું પેલે ન કરાય લાઈફ કોઈ તો પાણી લેતા જા તમને શું લાગે?
Sahil, can you mute yourself?
તું આ નખીએ રૂક 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 ભાઈ રૂક. હેલો.
Yes, can you mute yourself? Thank you. No, good afternoon. Namaskar.
Oh, good afternoon. Yes. You can hear me?
Yeah. All fine?
Yes. Yes, all good. All good, except last evening I was coming back from Lyon by train to Geneva, which is about 2 hours by train. So I was to get down in Belgrade, and the train was so crowded. It's like Mumbai local train almost. I went inside and I was feeling so claustrophobic. Just 5 minutes, 4 minutes before the train was supposed to start, I said, I'm going to get out of the train. I can't stay here. It's so crowded. But somebody next
Oxygen supply level is also low.
Yeah, somebody next to me, we opened the window, removed the jacket, and then then had some water. Then many people, in fact, in other compartments, not they had trouble. So somebody says, Akash Paul. Yeah, Akash, check your side speakers. You can all hear me? Sudipto says Bose Institute. Yeah, okay, excellent.
Yeah.
Excellent. So we wait for a minute, we start. So we have a good number of participants. We start in a minute then.
The participant number will increase with time because still our laboratories are running. Students are there. So
Let me see if Despina is down there, but she has joined. She's setting up to Bose Institute Calcutta is the host. Wow, that's good. So Bose Institute Calcutta, whoever is handling, in case we need, you have to help. Okay, so Raghunath, what we start right away?
I think Supriya is speaking something.
Yeah, you can mute yourself. Devassis Das, you can mute. There is a noise from somewhere. Okay.
Yeah, please mute
Devassis,
Devassis.
I'm not the host for some reason, so I can't. Mute people.
Yeah. So should we start, Tapanai?
Yeah. You can
Okay.
you can say a few lines and then we start.
Yeah, so for good evening, good morning, depending upon the position on the globe. So we have got to start, and before we start this virtual tour of Alice experiment, because we are going to start the run, and this virtual tour will be practically impossible. And thanks to Professor Tapan Naik for taking the lead from CERN, organizing this with Despina and other people, Roberto Divia, I guess, involved. So thanks to them for taking us a virtual tour.
Hi.
In fact, yeah, the Despina has joined.
Yeah, I'll try this.
Despina. Yeah.
But you've got a Mac option I think.
Yeah,
Option
so
I.
we,
Oh, okay. No. Option I. Where is it?
Despina, if you can mute, we are going to start.
The control I,
Mhm.
command I for the
I can do
anyway.
it even though I'm not the host, right? I still claim host. No,
Des-
I'm
Despina, can you mute?
yeah. So in fact, many people are from not from quantum plasma area. So this ALICE experiment is one of the marvels of science and technology sitting at CERN. Always it is not possible to make a physical visit, and even if you are at CERN, sometimes depending upon the situation, data taking mode or access is available or not. So sometimes we may not get the access to see the cavern, and we are fortunate today. Today is the last day. We can make a virtual tour, so our team can go with camera and show everybody. And for people who are not in high energy physics, just to tell you few words. So this is one of the largest experiments in the world, and works at the frontier of science and technology. And you will have a plenty of opportunity not only to see the experiment, although virtually, you will have the opportunity to interact with our experts and ask any questions related to science and technology. What are the fundamental issues this ALICE experiment is addressing? Okay. So with this, I thank our team from CERN and hand over the virtual dais to
Okay,
Professor
greetings
Tapan Naik.
from CERN, greetings from Alice. So the plan for today right now, I have 30 slides. So I'll take about 25 minutes. So then with me, we have Despina and Roberto Dibia. They are in the control room downstairs. I'm sitting upstairs. Where control room data taking is going to start this very soon. So preparations are going on. So I didn't want to disturb them with my voice and your questions, if there is any. So let me start with my slides. Beforehand, let me thank Raghunath and also director of IIT Indore to initiate this. He was here 2 weeks back. So to initiate the virtual tour today. So today is the last day we can go down with a camera it is not the
Recording in progress.
okay. So the visits to the LHC cavern, LHC and the experimental cavern are completely closed right now. Only with a proper dosimeter and with proper impact, proper permissions, 1 or 2 persons can go down till this evening 10 o'clock. After that, things will be closed in preparation to start the beam time. So let me share my slides. My slides are in the Indico page. So let me share screen. Share. Just tell me if you can see my slides.
Yeah, perfectly all right. You can please go.
How did you got the number?
Yeah.
You mailed it.
Okay, so welcome to CERN, welcome to Alice. This is the title I gave for today. Just to give a brief introduction to CERN and what we do in Alice. This left side picture is the Big Bang picture which you see in any time you type on the Google, you type Big Bang, you'll see this type of picture. I'll come over to that. Right side a picture of the Alice cavern. Today what you'll see is not this open cavern, you will see the magnet. The red is the magnet, the doors will be closed. Doors are closed in order to prepare for the beam. Beam is coming within few days. So, but you will see, you will get a feeling of what's going on underground. To start with, let's see, okay. So this is CERN. This is a view of CERN front side, which was taken like more than a year back. The view is slightly different right now. There's a new science gateway coming up on the both sides of the tram line. So it looks very different. The construction work is going on. But this is the CERN globe, which is the famous globe. It's a big dome, auditorium, plus exhibition complex. And the right side is the reception. And these white ones were this one was taken in 2019 during the open days. And after that, things have changed right now. So CERN is the European Center for Nuclear Research. So this is where the science happens without borders. So it is situated in Geneva. The main offices are in the Geneva, but in the border of France and Switzerland. In Switzerland, you have 1/3 of the big large collider, which I'll show. The 2/3 is in the Swiss side, in the French side. So most of our offices are here. In fact, on the Swiss side, the experiment, our experiment, Alice experiment is in the French side, where I am sitting right now on the French border in Saint-Denis on the French side. But there are people from all over the world who work at CERN, almost all countries. And there are member states. There are 23 member states, about 5 to 7 associate members. Then there are observers. These are different status given to the different countries depending on their participation, contribution. So mostly European countries are the member states. Then there are associate member states and the observer states. And then there are many countries who are participants without any particular portfolio. The science, CERN was established in 1954. It has become a prime example of international collaboration. Its mission is to perform world-class research in fundamental physics. Fundamental physics is the main fundamental physics, and nuclear high energy physics are the main purpose, but it has huge component of engineering in addition to the fundamental physics. In order to have the accelerators and laboratories, you need large engineering. Can Indranil, can you mute? Indranil, can you mute? Yeah. Then it provides a unique range of particle accelerators that enable research at the forefront of human knowledge in an environment-friendly, responsible, and sustainable way. It unites people from all over the world to push the frontiers of science and technology for the benefit of humankind, trains new generation of physicists, engineers, and technicians, engaging all citizens in research and in the values of science. So outreach is and communications are one of the main avenues through which we reach almost most of the people who are interested in science and education. At CERN, our work is helping to uncover what the universe is made up of and how it works. Somebody is using the pens to write things. Can somebody? Subham, who is Subham? And Subham is speaking and somebody is writing also. Somebody is drawing on my slides. Who is that? Please stop drawing. Subham, who is speaking and somebody is writing also. Somebody is drawing on my slides. Who is that? Please stop drawing. Subham, who is speaking and somebody is writing also. Somebody is drawing on my slides. Who is that? Please stop drawing. Subham, who is speaking and somebody is writing also. Somebody is drawing on my slides. Who is that? Please stop drawing. These arrows are not my arrows, but whoever has done it, please remove it because it's the rest of the slides are going to be dark color and it shows up. I don't know whether I can remove it. Maybe not. Okay, let's continue. Let's because once I come to this universe picture, these lines look very ugly. Just a second. Whoever has drawn it, please remove. If I can remove. I don't know whether I can remove.
So in the chat, it writes Skinny Pandey was writing, and the host can disable the mic and other permission for others.
Yeah, I'm not the host. For some reason, I'm not the host.
I have made you co-host now after Bose Institute made me the host.
Okay, can you delete these lines because they look very. Who was typing this? I don't know who was typing.
Sir, it's written in the chat, meeting chat. Can you find this?
Chat.
Yeah.
Okay.
Kini, please don't do that because that is disturbing everyone.
Can you delete?
And,
Sir, only Kimi can delete this. Who has written, only those person can delete.
Who is that person? I don't know.
Kini, can you remove lines?
No, now you can, I think, delete this.
Who, Raghunath can delete?
So that stays in all slides or what? I don't know.
Yeah, it is staying in all slides.
Sir, you can do one thing, that you can start resharing the tabs.
Okay, so let me stop. That's a good idea. Thank you. Wonderful. So now it is okay?
Yeah.
Okay, thank you so much. I couldn't recognize the voice, but whoever said is nice. Thank you. Okay, so now let's start with our universe, how we got started, how the whole thing got started, and what the universe is made up of, where it is going, and how far we can understand the universe. That's the main goal of our fundamental physics in nuclear and high energy physics mostly. And if you start with the Big Bang, this is time t equal to 0. We are at the Big Bang, this dot here. And as time goes on, we are at 13.7 billion years after the Big Bang. Today, we are here at this point. If you go along the Big Bang timeline, a lot of things happen very quickly. Within a microsecond, many things have happened. If you look at the timeline, in the beginning, it is just a huge amount of energy at a dot, at a singular point. And then the universe expands very quickly. In the beginning, you have all the four forces, strong, weak, gravity, and electromagnetic, they're all united. And then they slowly got separated. And then within a microsecond, many things have happened. Just around a microsecond, the whole thing was made up of quarks and gluons. And then it hadronizes to protons and neutrons and all that. So these things we'll be studying. I'll come over to that in much more detail. So in order to understand the Big Bang, what is going on, this picture you see, this, I don't know whether you can see my mouse. This picture you see here, this is a picture taken 380,000 after the Big Bang. This is a picture taken by astronomical probes. The temperature variation picture, temperature fluctuation picture, which is 380,000 years after the Big Bang. And using the astronomical probes, we try to understand many things, but we are trying to use the accelerators. So the Big Bang conditions you can access in two different ways. One can access in terms of astronomical probes, like you have all the Hubble telescope, you have the James Webb right now, you have many satellite probes. You can understand the universe, what is going on. And then using the accelerators, like at CERN, the Large Hadron Collider, we are trying to go very smaller and smaller distances. This scale here gives the picture from size 0, starting of the Big Bang, till now, the universe today. At the beginning, size 0, like 10 to the minus 32 centimeter if you like. Right now, the diameter of the universe is 9 times 10 to the power 26 meters. So this is the universe at this point. You can see the proton size 10 to the minus 12 meters, atoms 1 angstrom 10 to the minus 8 centimeter, radius of the Earth to Sun, all these distances are coming up, radius of the galaxies. Using the astronomical probes, we are trying to understand the Big Bang conditions, also going to closer and closer towards Big Bang. But using high energy accelerators like the Large Hadron Collider, which is at CERN, you can try to understand in much more detail and go even much more closer to the beginning of the Big Bang, the conditions which existed in the beginning of the Big Bang. So if I put this in another way, this is the history of the universe. This is the different slices. You have the Big Bang time t equal to 0, as I told you. Then the whole situation changes. The energy is extremely high, and this very point-like system, the whole thing starts expanding greatly. And within about 10 to the minus 10 seconds, possible dark matter candidates also, dark matter helix also, 4 seconds, about 100 seconds, you have the nuclei formation, then cosmic microwave background radiation with the picture which you saw before, that is around 380,000 years after the Big Bang, when this beginning of the galaxies are starting to form. So using astronomical probes, we can mostly understand up to 380,000 years Big Bang, although there are different extrapolations with different satellite conditions now, which we can try to go even before that. But if we use the accelerators like the Large Hadron Collider at CERN, it can take us back to within a few microseconds of the Big Bang. After the Big Bang, the proton-proton collision at the Large Hadron Collider, we can understand the Higgs mechanism even very early on. Then the heavy ion collision, we can understand something called a quark-gluon plasma. Just after within a microsecond, just after that, the quarks and gluons, they form hadrons, like nucleons, like the quarks. Nobody has seen a free quark after that. So the heavy ion collisions, we are looking for something called a QGP, quark-gluon plasma. Even before that, we can understand using proton-proton collision what happened to the Higgs mechanism, which is responsible to give mass to the different particles. So these are the fundamental understandings we can have if you go to accelerators instead of the satellite probes. Just to one slide on the fundamental constituents of matter. Many of you would be knowing this. Those who are maybe undergraduate students, they will be studying this. You have, starting with the matter, you can start with the matter. Matter goes to smaller and smaller. If you go to smaller and smaller, you have atoms, you have molecules. You go inside the molecules, you have atoms. Inside the center of the atoms, you have a nucleus. Surrounding the nucleus, you have electrons. Inside the nucleus, you have protons and neutrons. And protons and neutrons were thought to be most fundamental for for very long time, till like beginning of 1970s. And that time, the theoretical calculations came up with the idea that protons and neutrons, they are not most fundamental. They are made up of quarks. And the quarks were discovered in deep endless scattering experiments in Stanford Linear Accelerator Laboratory Center in US. And the quarks, right now, the present understanding is that the quarks are the most fundamental constituents of matter. You have 3 different kinds of quarks: up, down, charm strange, top, bottom quarks, up and down. These are, now we're starting to go to heavier quarks like charm and strange, then top and bottom. And top quark is very heavy. They are heavier quarks. Then you have the leptons, electrons, muons, and tau, and their corresponding neutrinos. Then there are force entities like photons, which carry electromagnetic force, gluons, which carry the strong force, and W bosons and Z bosons, which carry the weak force. Then at the center of all that, the picturization here is the Higgs boson, which is responsible for giving mass to all the particles. The understanding the primordial state of matter after the Big Bang, before the protons, is, let me see, this goes, no. Okay, one step back, one step back. What happened now?
Sahil, can you mute yourself? Sahil?
Understanding the primordial state of matter after the Big Bang, before the protons and neutrons are formed, the primordial state is called the quark-gluon plasma. This is one of the fundamental goals of our program at CERN. Understanding the Higgs mechanism, which is responsible for giving the mass to all the particles. This is a big study at CERN. The 2012, the Higgs discovery, and followed by the Nobel Prize for the Higgs. These are the one of the most important milestones in CERN's history. Finding the reason why the antimatter and matter did not completely destroy each other, why there is only matter right now, why there is no antimatter. This is another way. Then there are a lot of studies going on the dark matter candidates and also standard model and beyond standard model physics. So these are mostly the physics-wise what is going on at CERN. Now, other than the physics, the CERN has come up with a lot of different technologies which are useful to all of us. One is the WWW, the World Wide Web. This is in 1990, Tim Berners-Lee. So this is a picture where the web is born. Other than that, we have capacitive touchscreen. Our phone touchscreens, for example, the touchscreens. This is a technology from 1970s with the capacitive touchscreens. This is a Frank Beck and Bent Stump. The engineers at CERN, they developed a capacitive touchscreen to control the accelerator parameters. So this is very similar to what we are using right now with a much more improved version, of course. Then there are a lot of huge medical applications, including positron emission tomography, PET technology, and many, many more spin-offs like the hadron therapy, nuclear therapy, and all that. So today I'm not going to get into all the spin-offs and all the technological things. We'll concentrate on physics, and then now we come to Alice experiment. The Large Hadron Collider, as you may be knowing, this is a large, this is a 27-kilometer tunnel, and the tunnel exists about 50 to 100 meters below the ground, and 1/3 is in Switzerland, 2/3 is at the on the French side, 50 to 150 meters below the ground. The two beams, they circulate in opposite directions. Beams are energetically charged particles, like either protons or xenon or mostly lead, mostly protons. Then we have lead-lead collisions. The beams move at the speed of light in these tubes. These are tubes of magnets, and the RF, radio frequency. The radio frequency gives a kick, so the particles move faster and faster. The magnets put them in a track. So these are circulating beams in opposite directions. They collide at different points, at 4 different points, where we have the big experiments. In total, we have 9,300 or maybe more magnets in the whole thing, and 1,800 large superconducting magnets, which constitute the Large Hadron Collider. One of the pictures of the Large Hadron Collider, the aerial view is like this, and you have the Lake Geneva. That's the airport runways. And the beam, basically the charged particle beam starts from this MERA labs. Slowly, the beam energy going up and up and up. Then there is this SPS, superproton synchrotron. Then the big one is the Large Hadron Collider. The lines were actually drawn. This picture was taken, the lines are drawn to indicate where the Large Hadron Collider and different beams are. The SPS is already 7 kilometers, but this one is 27 kilometer large ring. Okay, the mountains on both sides, the Jura Mountains, there's a lake, and the Alps are on the other side. Now, there are 4 major collision points. There are 9 experiments which run at Large Hadron Collider, 4 large experiments. The 2 experiments, Atlas and CMS, they discovered the Higgs particles, and the Nobel Prize came the year later in 2013. LHC-B experiment is looking for why there is no antimatter, why only matter survived, there is no antimatter. They're looking for matter-antimatter asymmetry. B is for beauty physics, B quark. And then the ALICE experiment, which we are going to see today, and also the physics I'm going to discuss right now, is looking for the quark-gluon plasma, which I talked before. Coming to the ALICE experiment, this is a picture from the front, not inside. This is a picture when you enter the building. This picture was taken last year in one of our get-togethers. The main goal is to study the quark-gluon plasma, basically journeying through the beginning of the universe, as I said, within a microsecond after the Big Bang, or within a few millionths of a second after the Big Bang. Our collaboration, the ALICE, a large ion collider experiment, the ALICE, a large ion collider experiment collaboration, has built a dedicated detector to study this matter at extreme conditions of temperature and energy density by colliding proton-proton as well as lead-on-lead, heavy ions. The properties of such state, once we have discovered it, we are trying to study in much more detail. They give the key issues, they provide key issues for understanding quantum chromodynamics. Chromo is for the color because the quarks have some color degrees of freedom. Now, why we make heavy ions instead of proton-proton? The proton-proton consists of 3 quarks to 3 quarks. We want to create a conditions of quarks and gluons, a large system of quarks, 3 quarks and gluons. So we start with heavy nuclei like lead on lead. So this is a picturization when one lead ion collides with another lead ion. So large number of particles are coming out. So we take a high mass like lead, take away the electrons, makes a heavy ion, accelerate the ion to the speed of light, then collide them, then study the aftermath by detectors, like in our experiment, ALICE experiment. In fact, all 4 experiments, they have the heavy ion program, but ALICE is specialized on this one. Other experiments are specialized in different topics, but they have a good program of heavy ions, but ALICE is dedicated heavy ion experiment. The detector, in fact, looks like this, but you will not see this today because I'll explain to you. The red one is a magnet, the red one. So the beam, in fact, in this picture, the beam goes towards the screen from one side, coming back from the other side. There's a collision happens at the center. At the collision, many thousands of particles are coming out, up to 20,000-30,000 particles are coming out. These particles can be electrons, protons, pions, kaons, photons, all types of fundamental particles, not quarks, because quarks very quickly they form hadrons, protons, neutrons. So quarks are formed, quarks collide, but when the particles we measure, they're already quite late. The quarks don't survive that point. So only protons and particles like that, and some stable, non-stable particles like that. So at the collision point, we have series of silicon layers, and this silicon layer, they measure the vortex.
Just changing an introduction.
Margie, can you mute your microphone, please? Yeah. So the collision happens, And surrounding the collision point, we have a series of silicon detectors. They measure the collision point, and they measure also the particles, number of particles coming out. Surrounding that, we have a time projection chamber. This blue one is a big, large gas volume where we have the gem detectors as readouts on the sides. Then after the TPC, we have the transition radiation detector, time of flight detector. Then we have the electromagnetic calorimeters on this side. And there are forward detectors. And there are series of trigger detectors. We have scintillator detectors, we have quartz detectors, crystals, that are trigger detectors. And the other side, which you don't see in this picture, are the muon spectrometer, where you measure specialized muons. Now, this collaboration, this is a picture from last month. We have 40 countries in the collaboration, 171 institutes, and close to 2,000 members. Out of the 2,000 members, there will be 700, 800 will be our students, and then we have scientists, engineers, physicists continuing. So much more on this ALICE collaboration. You can go to alice.cern and click on alice.cern. You have a lot of information about the collaboration, about how it works, the physics, the experiment. There are a lot of videos in the alice.cern. In one collision, lead-lead collision at 5.002 tera electron volt, so this 1 peta electron volt collision, you see so many types, so many particles are coming out. This is one collision. These particles, they bend because of the magnetic field. The charged particles, they bend. The photons measurements are a little different, tricky, but the charged particles, they bend. They make beautiful pictures like this. And from these particles that are coming out, we try to recreate what had happened in the beginning of the Big Bang. We reconstruct the collision or recreate the collision. So that means we want to find out what has happened. So during when the data taking is going on, during the data taking, we have a control room downstairs, and we try to monitor the data quality, calibrate the detectors. Using the trigger, we keep events which are of interest, and then send to data storage. Offline, after the storage is done, offline, we do the event reconstruction. We find out vortex, where the collision has happened. We do the tracking. We do the particle identification, try to find out whether it's a proton, neutron, charged particle, proton, all that. And then we reconstruct somebody. Sanju, your microphone is on. Can you please mute? Sanju. So then these particles are coming out. We measure that. The conditions which happened within a microsecond after the Big Bang, Bose Institute, that conditions are high temperature, high energy density. So I'll give you only two examples today, just to show that we have the conditions which is similar to the Big Bang. This is a collision which is happening. You have a lead ion. Lead, when it is moving at the speed of light, so Lorentz contracted, is like a pancake. They collide, and a lot of things happen. You have a quark-gluon plasma, hadrons, many particles are coming out. We have picturization like this. From this picture, in fact, we can go back and try to study at each stage what had happened till the time of the collision. So first thing we measure is the number of particles which are coming out. Then we have, when the collision happens, collision can be central collision, head-on collision, or a peripheral collision, grazing collision. Then the total number of particles in a head-on collision can be up to 25,000 number of particles. It's very, very large number of collisions in one number of particles in one collision. So in each second, we have many thousands of collisions data we are taking, and the data is stored. Many of the students, young students, they just do the data analysis after the data is taken, and using sophisticated computer technology and publish beautiful physics results. Using the number of particles, we can estimate the energy density which is formed in these collisions. This energy density, what we have seen, is about 15 or 20 GeV per Fermi cube. GeV per Fermi cube, that is very, very high energy density, and it's about 10 to 20 times more than the normal nuclear matter density. This energy density is much higher than the critical density for the formation of the Big Bang, formation of the quark-gluon plasma. That means we have formed a quark-gluon plasma which is very, very highly dense. One more example in this respect is the temperature. And we have, as I told you, in the beginning of the Big Bang, we have very high temperature, high density. And the temperature at the core of the sun, right now, if you look at, is 27 million degrees Celsius at the core of the sun. The temperature we measure from photon spectra. Photons are the electromagnetic particles which are coming out of the collision, or very high energy gamma rays. As a function of their momentum spectra, if you measure, the PT spectra looks like this. You feed this spectra, you get a temperature of 3527920 million degree. Compared to 27 million degree, it's very, very high. So we get something like here 304 million electron volt. 1 electron volt is 11,605 Kelvin. So we have like 3 million degree, very, very high temperature. So only two examples I am giving you today. If you are interested, if you go to alice.cern, you will see a lot of examples where we can tell you that we have formed the quark-gluon plasma. Now our major effort in next years is to understand the quark-gluon plasma is much more detailed. This is largest ever temperature reached in the laboratory. Just to give you a couple of examples of technology, last 2-3 years we have been working on, since last 2-3 years we have been working on our new silicon detector system, and which is just surrounding the beam pipe. This is the beam pipe. The beam travels in this one, collision happens at the center, and the particles are coming out. Then we have very high resolution silicon detectors. These silicon are based on CMOS monolithic cameras, like we have the cameras on our phones. These cameras use, we talk about 100 megapixels, and we have 12.5 gigapixels in the silicon detectors. We have 10 meters square of these cameras, this type of cameras, 10 meters square, and with 12.5 gigapixels, which measure the charged particles which are coming out from the collision, and very, very high resolution detector. And some of the pictures of the system, they look beautiful, photographs of the inner side and the outer side, and we have also the forward direction. So inner, outer, and then the muon forward tracker. This is seen in this picture. This is the beam pipe, in fact. Similarly, we have time projection chamber, and we have new GEM detectors in the TPC. The GEM detectors are on the sides. You see here on the other side, and the whole thing is filled with inert gas like neon. Filled up. You see the sides of the time projection chamber. So another view of the time projection chamber when it was going inside the Alice cavern. Despina will show you in few minutes this one. Not the TPC. She will show you only the cavern. She will be standing here. The TPC is already inside. You won't be able to see it, but you'll get an idea what it is. Another new detector which we put last year is called a trigger detector, fast interaction trigger. It has scintillators and it has quartz crystals, and it has the trigger. It gives you the luminosity of the beam, an indicator of the vortex position, and a multiplicity detector in the forward direction. This is what the view when the whole detector is closed. But on top of that, we have the concrete also on this one. You'll not be able to see all the fine details inside. The concrete blocks are in place for the data taking right now today. Just one slide, just showing that the future of the Alice experiment is quite bright. It goes to another 15-20 years. We have a beautiful planning. The new detector coming up in 2035 using all silicon detectors, in fact. Now, my last slide. So I started with the Big Bang. The Big Bang starting from time t equal to 0 here. That was a horizontal picture. This is a vertical picture. Time t equal to 0. And present day looks like this one on the last. Then inside we have a cosmic microwave background radiation picture by WMAP. This is the beginning of the galaxy. We want to create a picture which is similar to this one in our little bang. At the end, we measure something like this one. This one, we want to go back and see what happened in the little bang. The Big Bang itself is a one big event, one collision, what had happened 13.7 billion years back. Now in our accelerators, we collide billions of events. We take data, billions and trillions of events, small little bangs. Using that one, we are trying to understand what is there in the Big Bang. So with this short introduction to CERN, very brief introduction to CERN, very brief introduction to ALICE, and the ALICE on the left side, you'll see ALICE, which is partly open. You could have seen something inside like this, but today it is not open, it is closed. We'll see something like this, even with the more concrete. With this one, let me hand it over to my colleague Despina. She's downstairs. I'll go and meet her downstairs. She will take you to the underground. She will take you step by step. She'll show you how she's entering the cavern. She'll show you, she'll go underground in the elevator. Then she'll climb up and show you the detector and give you a brief. Then we come back after that with, if you have some questions, we'll come back after that. Is that okay? We'll do this way? Raghunath? Okay. Okay, we do this way. So Despina, if you are online, let me stop sharing. I think the most interesting part is for Despina to show underground. So we have close to 100 participants at least here. So I'm going to Despina. Okay, let me go down.
I think Despina is speaking, but we cannot hear her.
Now see, her microphone is muted. Okay, I'm going to go down, and then my laptop is here, but I'm going to I'm going to go with my laptop down. So I will tell her that we are ready to go down. Give me a few seconds.
Despina, mic has some problem, so both are open, but we cannot hear her.
No, I see mic closed. Anyhow, let me go down.
So she's using Alice at LHC point 2.
Okay. Okay. This will be with a telephone in fact. So you'll go down with a telephone.
Hello?
Yeah, Despina. Hi, Roberto.
Yep.
Hello, can you hear me now?
Yeah. I can hear you.
I don't know what the problem was before. Okay, so for the moment I'm in the control room, and soon I will go down. You can see already a view of the control room. This is there is also another account called Alice Run Control Center, where you can see the whole thing. Okay, so now I will go down. Let me see. So you have to do something to give me a key when I go in, okay? To allow a key, thanks. I've done it. Yes. Yes. Thanks. I have put my name here.
Okay, I need your phone number.
Oh, that was a different paper. I put on a different paper.
Okay.
One moment. There is a certain procedure. Okay.
This one. Okay, yes.
You can put that down.
I will.
Okay. Okay. So maybe Tapan told you already. Today and tomorrow are the last days that we have access to the cavern. After that, it will close, getting ready for BEAM, which will be end of March, beginning of April. Anyway, for what is valid now, we are, can you hear? We expect the first collisions beginning of April. What you see here is the big hall from where everything has come, and with the crane that you see, this yellow structure, everything that's in the cavern has gone down. So now the procedure to enter and go down to the Alice cavern is that we open the door with our personal dosimeter, which we see here, and then we have to take a key also. Okay. So I have to open the door with the key. No, no, what happened? Then we have to go through the biometric control, which is the control of the iris, so that the system verifies that the correct person enters, and then I can take the lift to go down. Alice is at a depth of 51.2 meters below ground. You can see the lift coming up. The Large Hadron Collider is in a tunnel which is at an average depth of 100 meters, but in reality this tunnel is slightly inclined, and here where we are at point 2, this is the less deep point. The lift goes down very fast, of the order of half a minute. It might be that the connection is lost momentarily, but not necessarily. So let's see. You can watch while it's going down.
I think ma'am has left the meeting.
No, within the lift, actually, the connection may be lost, but don't worry. So just matter of few seconds.
Can you hear me? I don't think the connection was lost, but I couldn't hear you.
Yeah, now we can hear.
You can hear. Okay, so now I'm out of the lift. At this level, you can see various installations which are needed for cooling all the electronics of the experiment. And now I will go up some flights of stairs and place myself on a platform in front of the central part of Alice. This big octagonal structure, which is a solenoidal magnet, which contains most of the detectors of the experiment. Afterwards, I will go to the other side, where you can see the mu spectrometer, which is sort of a piece apart. So this cavern where ALICE is installed, exists since 40 years, I would say, because in here, before ALICE, there was another CERN experiment called L3. That was at the times of LEP. LEP was a large electron-positron collider that was installed inside the tunnel that is now used for LHC, and that was before LHC. LEP collided beams of electrons with beams of positrons during the period 1989 until the end of 2000. So in here, there was one of the 4 LEP experiments, L3, and from this experiment we inherited this big red magnet. So this recycling made the cost of ALICE, at least the initial cost, a little bit lower than the other experiment. And this magnet is actually a conventional magnet, meaning it is not superconducting like the magnets of the LHC itself or of 2 of the big experiments, ATLAS and CMS. This is a conventional magnet, water-cooled, so it consumes something like 4 megawatts. So as I imagine Tapan has told you, the size of ALICE is 16 meters high, 16 meters wide, and 26 meters long. So you can consider it something like a 5-story building. And it weighs 10,000 tons. A big part of the weight is the iron from this magnet, and also the other magnets from the spectrometer that we'll see afterwards. So you see here the big tubes are for ventilation. Inside the magnet, there are many detectors. Many of them are gaseous detectors, which means there are different gas mixtures going in. You can see here all these stainless steel tubes bring the gases from the surface to here, underground, and then inside the magnet to feed the different gaseous detectors. So since there might always be a slight leak of gases, the space inside the magnet has continuous ventilation. The same applies for the cavern. Since it's a closed underground area, there is always ventilation. You see the big tubes, and this makes it also quite noisy. So in here, there are most of the detectors. You've seen already from Tapan about the various detectors. I don't know if you can see here. If the door was open, if the doors of the magnet were open, you would see something like this. But we don't open the doors very often because this is an operation that takes a long time. To do this, we would need first to remove these concrete blocks that surround a big, yes, I will go afterwards around, sure. We would have to remove these concrete blocks that shield a support frame that is here in front of ALICE, which also has a compensator magnet, a small dipole compensating for the magnet which is on the other side. And then the actual opening of the doors, which weigh 300 tons each, takes many hours. So we don't do it every day. So to have a full view of the cavern, here you can see on the 2 sides there is a sort of balconies where there is a lot of equipment. For example, power supplies or other electronics, maybe distribution of gases to the different detectors and so on. Let me see. Right now I'm exactly under the shaft. I am under the shaft, and you see that it is closed with concrete. This is to stop the radiation going out when there is beam in the accelerator. You also see a crane here. This takes the whatever comes down from the surface with the other crane and moves it all the way to the magnet, and then normally we have special tools for the installation of the detector. There was a question about why the magnet is classical and not superconducting. Well, this is a technology that was used something like 40 years ago. At the times of LEP, if I'm not mistaken, only one of the LEP experiments had the superconducting. This means that the magnetic field is not as high as for the other LHC experiments. Others and CMS have a superconducting magnet which produce 4 Tesla. Here, field is half a Tesla, but this is okay, can go down to low PT, which the other experiments cannot do. Obviously, it was judged that this magnet is suitable for ALICE when it was decided to take it from L3. By the way, the other magnet that you will see when I go to the other side is also classical. That's a dipole of with a field of 0.6 Tesla. And the whole consumption of power in ALICE is of the order of 10 megawatts, which is a good chunk of the whole of what the whole of CERN consumes when the accelerators and the experiments are on, which is 180 megawatts, the equivalent of what Geneva consumes. Behind this wall is the LHC tunnel, and under my feet is the last triplet, the last magnet of LHC, which does the final focusing of the beams, because when they enter in collision, they need to be as much focused as possible in order to increase the probability of doing collisions. So there is a question with higher temperature won't. Oh, I missed it. Is it a single electromagnet? I don't know what it means, single. Yes, it's single. I mean, there are double magnets for the LHC, where there are two beams to be guided. But here we just have one magnet. Okay, the other is on the other side for the muon spectrometer. But this is just one magnet to curve the trajectories of particles which are produced from the collisions. By the way, the collisions happen inside this thing, I would say at a distance of something like 6 meters from the outer surface that you see, the outer surface of the magnet. So let me now go to the other side, to the muon spectrometer. As you will see, has a different geometry. The central part of ALICE is made of detectors which have cylindrical geometry and which surround each other, like the various layers of an onion. The muon spectrometer has a forward geometry, which means that the detectors are one behind the other. They are, we could say, slices. This means that we cannot cover everything. We just cover a certain angle for the detection of muons. Actually, this is the geometry that one of the 4 LHC experiments has, the experiment LHCb, where the collisions do not happen in the middle like in the others, but in front of the experiment. So I'm now walking in a corridor, a narrow corridor, which goes in parallel to the solenoidal magnet. And eventually I will be on the other side. You will see here various cables. Actually, many of the visitors who visit Alice are impressed by the huge number of cables that is used for everything, for high voltage, for bringing out signals, for feeding the electronics and so on. Here, these tubes that you see, bring the water to the magnet for cooling it. So here you see part of the big dipole, well, most of it. The big dipole which is here to curve the trajectories of muons upwards or downwards, depending on the sign, if they are positive or negative. The blue thing is iron that closes the magnet, the magnetic field. You see one of the poles of the magnet. You see the tubes for the water for cooling.